Hi everyone, welcome to my presentation. I am Dr. R. Purnima, Assistant Professor, Department of Mathematics, Hindustan College of Engineering and Technology, Coimbatore. Today we are going to discuss about the applications of matrices. This video actually the continuation of the previous video. The last video we covered the topics of power of matrices, orthogonal matrices, approximation of eigenvalues, diagonalization. So in this session, we are going to cover that applications, that is cryptography, an error correcting code, method of least squares and discrete compartmental models. Let's start this session of cryptography. A cryptography is a secret writing. It means code. A simple code is called that the letters A, B, C, etc. Z be represented by the numbers 1, 2, 3, etc. 26. A sequence of letters can then be a sequence of numbers. Arrange these numbers into an m by n matrix M. Then we select a non-singular m by m matrix A. The new sent message becomes y is equal to A into m. Then m is equal to A inverse y. Next, we move on to error correcting code. Parity encoding, that means add an extra bit to make the number of 1 is even. We just move on to the example. So we consider W is equal to 1, 0, 0, 0, 1, 1 and the next subdivision W is 1, 1, 1, 0, 0, 1. Now, the extra bit will be 1 to make the number of 1 is 4, that is even for the first subdivision. So, the code word is then C is equal to 1, 0, 0, 0, 1, 1, 1. We move on to the next subdivision. The extra bit will be 0 to make the number of 1 is 4, that is even. So, the encoded word is C is equal to 1, 1, 1, 0, 0, 1, 0. That is, the message is encoding, that is a code word. Then transmission is applied, will be receiving a message. Then decoding, after that decoded message or error indication will be received. We move on to the next example, decoding the following. That is subdivision A R is 1, 1, 0, 0, 1, 0, 1. And for subdivision B, R is equal to 1, 0, 1, 1, 0, 0, 0. So for the first case, the number of 1 is 4 even. We just drop the last bit to get 1, 1, 0, 0, 1, 0. For the second case, the number of 1 is 3, that is odd. So it is a parity error. Next, we move on to the Hamming code, that is W is equal to W1, W2, W3, W4 and C is equal to C1, C2, W1, C3, W2, W3, W4, where C1, C2 and C3 denote the parity check bits. Encoding C1 equal to W1 plus W2 plus W4 and C2 equal to W1 plus W3 plus W4 and C3 equal to W2 plus W3 plus W4. So we convert this into a matrix form. C1, C2, C3 is a column matrix which is equal to 1, 1, 0, 1, 1, 0, 1, 1 and 0, 1, 1, 1 into the column matrix W1, W2, W3, W4. So we consider the example, encode the word W equal to 1011. We are solving this one. W1 equal to 1, W2 equal to 0, W3 equal to 1, W4 equal to 1. That is, the column matrix C1, C2, C3 equal to 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1 is multiplied by the column matrix 1, 0, 1, 1. After applying the matrix multiplication, we will be getting that 0, 1, 0. That is C1 equal to 0, C2 equal to 1, C3 equal to 0. So C is equal to 0, 1, 1, 0, 0, 1, 1. Next, decoding. we are using this concept for the decoding one, that is S is equal to H into R transpose, that is equal to 0. We move on to the example. Compute the syndrome of subdivision A. It is R is equal to 1, 1, 0, 1, 0, 0, 1 and R is equal to 1, 0, 0, 1, 0, 1, 0. So the solution is S is equal to a matrix is multiplied by the column matrix, that is 0, 0, 0, 1, 1, 1, 1. The next row it is 0, 1, 1, 0, 0, 1, 1. The third row it is 1, 0, 1, 0, 1, 0, 1, which is multiplied by the column matrix 1, 1, 0, 1, 0, 0, 1, which is equal to 0, 0, 0. It is also a column matrix. So we conclude that R is a code word. So we get the decoded message. Next we move on to that. S is equal to a matrix is multiplied by the column matrix, but the equivalent value is 0, 1, 1 here. So since S is not equal to 0, the received message R is not a code word. Now we consider E is equal to E1, E2, E3, E4, E5, E6, E7. So EI is set of all 1 if noise changes the ith bit. Suppose 0 if noise does not change the ith bit. That is, R is equal to C plus E, that is R transpose equal to C transpose plus E transpose. Therefore, H into R transpose equal to H into C transpose plus E transpose, which is equal to HC transpose plus HE transpose, which is equal to 0 plus HE transpose, that is HE transpose. Therefore, HE transpose is equal to E4 plus E5 plus E6 plus E7. The next row E2 plus E3 plus E6 plus E7 and the next E1 plus E3 plus E5 plus E7. So H into E transpose is E1 into the column matrix 0, 0, 1 plus E2 into 0, 1, 0 plus E3 into 0, 1, 1 plus E4 into 1, 0, 0 plus E5 into 1, 0, 1 plus E6 into 1, 1, 0 plus E7 into 1, 1, 1. That is, R is equal to 1, 0, 0, 1, 0, 1, 0. That is, S is 0, 1, 1. Changing 0 to 1 gives the code word C equal to 1, 0, 1, 1, 0, 1, 0. Hence, the first, second and fourth bits from C, we arrive at the decoded message 1, 0, 1, 0. So, we move on to the next topic, that is method of least squares. If we have the data 1, 1 or that is ordered pairs 2, 3, 3, 4, 4, 6 and 5, 5, we want to fit the function f of x is equal to ax plus b. Then a plus b equal to 1, 2a plus b equal to 3, 3a plus b equal to 4, 4a plus b equal to 6 and 5a plus b equal to 5. That is, let y is equal to 1, 3, 4, 6, 5 is a column matrix and also a is equal to 1, 1, 2, 1, 3, 1, 4, 1 and 5, 1. So, we have A transpose A is 55, 15 and 15, 5. So, x is equal to 55, 15, 15, 5 the inverse into 1, 1, 2, 1, 3, 1, 4, 1, 5, 1 transpose is multiplied by the column matrix 1, 3, 4, 6, 5. So, after multiplying all these things, we will be getting 1.1 and 0.5 as a column matrix. So, we have Ax equal to y, then the best solution of x will be x equal to A transpose A, the whole inverse into A transpose into y. For this line, the sum of the square error is E is equal to 1 minus f of 1 the whole square plus 3 minus f of 2 the whole square plus 4 minus f of 3 the whole square plus 6 minus f of 4 the whole square plus 5 minus f of 5 the whole square, which is equal to 2.7. The fit function is y is equal to 1.1 into x plus 0.5. So this represents the figure. So you can just see the diagram, you can able to understand the concept. Next, we move on to the next topic, discrete compartmental models. So the general will be having two compartmental model, dx by dt equal to minus of f12 plus f10 into c1 of t plus f21 c2 of t plus I of t, and dy by dt equal to f21 c1 of t minus f21 plus f20 into c2 of t. So this diagram represents the compartment model 1 and compartment model 2. Next, X is equal to the column matrix which is represented by x1, x2, etc. xn, and Y is represented by the column matrix y1, y2, etc. yn. So y1 equal to x1 plus amount of tracer entering 1 minus amount of tracer leaving 1. That is 1 minus tau 21 minus tau 31 minus etc. tau n1 into x1 plus tau 12 x2 plus etc. plus tau 1n xn. So y1 is tau 11 x1 plus tau 12 x2 plus etc. plus tau 1n xn, etc. yn is equal to tau n1 x1 plus tau n2 x2 plus etc. plus tau nn xn. So we represent this in a matrix form. y1, y2, etc. yn is a column matrix equal to tau 11, tau 12, etc. tau 1n, etc. tau n1, tau n2, etc. tau nn is multiplied by the column matrix x1, x2, etc. xn. So compartment I indicates that tau ji to compartment j. Then from compartment j it indicates that tau ij to compartment I. So the initial amount is 100, 250, 80 for these three compartments. For compartment 1 C1 20% to C2. Then 0% to C3. Then 80% to C1. So for C2 5% to C1 and 30% to C3. Then 65% to C2. For C3 25% to C1 and 0% to C3. Then 75% to C3. So you are representing all these things in a T matrix form. So this represents this diagram. We just apply the values in that diagram. So that is now C1 equal to 0.8 C1 plus 0.05 C2 plus 0.25 C3. Then new C2 it is 0.2 C1 plus 0.65 C2 plus 0 C3. And new C3 it is 0 C1 plus 0.3 C2 plus 0.75 C3. So we get the transfer matrix as T, that is 0.8, 0.05, 0.25. The next row it is 0.2, 0.650 and 0.3075. So 1 day later y is equal to Tx, that is T is multiplied by the x matrix 100, 250, 80. After applying the matrix multiplication we get the resultant matrix. It gives that value 112.5, 182.5 and 135. So m days later y t to the power m into x naught. That is x1 equal to t x naught, x2 is t x1, etc. xn plus 1 equal to t xn. Therefore, xn equal to t to the power n into x naught, where n lies between 1 to 3, etc. to infinite number of terms. Now we are just saying that representation of this diagram. Grasses leaching to soil, soil to, that is soil growth to grasses. Then grasses, it's death to dead organic matter. Then dead organic matter decomposition to soil. Then soil from runoff to streams. So x naught is 20, 60, 15, 20 and t it is 0.85, 0.01, 00, 0.05, 0.98, 0.20 and 0.10, 0.80, then 0, 0.0101. So x1 is t x naught. We just apply that value of the T matrix and x naught matrix. After applying the matrix multiplication, we will be getting the resultant matrix, that is 17.6, 62.8, 14.0 and 20.6. So we complete that presentation. Thank you for your attention. Thank you very much.